assistant professor at MBZUAI. How do you say this? Do you actually say MBZUAI or his research focuses on providing a fundamental understanding of how distributed and federated training algorithms work and how they interact with different sources of heterogeneity. Also, by the way, Samuel, along with Peter and Sebastian, run the Federated Learning One World online seminar, the FLOW seminar. It's an excellent resource, which is like a ton of talks. Highly recommended for everyone to check it out. Thanks.
Thank you, Brian, for a great introduction. So today what I want to speak about is this work titled Fair and Accurate Federated Learning under Heterogeneous Targets with Fourth Dropout. Let me first acknowledge my wonderful collaborators. This is Steve, Mario, Stelios, Ilias, and Nick. Well, all of them at the time when we were writing the paper were at Samsung AI Center in Cambridge. I'll discuss a bit motivation about the federated learning, although I don't think I need to, but I just want to a bit motivate the problem that we are focusing on. So traditionally, let's say in machine learning, we implement knowledge by, or how we used to do it, we just collected all the data in one centralized location, but over the time, we just moved from centralized to cloud-based solution as much machine learning sciences relies on two things. One is that we have large-scale training infrastructures and also the vast amount of training data. But there is a catch to that, and it's the majority of data, it comes from users. And it might have, for users, this might have quite a negative experience because of the privacy leakages in terms of their data. So what we usually, on top of that, there are several privacy initiatives enforced by both government entities and also some private companies that at the end of the day, what might happen is actually that we lose this access to the data and we lose one of these two pillars of success that we see in machine learning. Thankfully, so several years back, federated learning was proposed to kind of alleviate this issue of losing access to data, which was by bringing the training to the edge devices. And those devices are only allowed to communicate some gradients or aggregated informations, such that there is a hope that once we lose the access to the data directly, we can guarantee some kind of privacy. And maybe this combined with different cryptographical techniques or differential privacy, that should give us at least some notion of privacy. And also, I think there are a few studies showing that actually federated learning as itself, like by obeying the data locality paradigm, you can have a lower carbon footprint when compared to cloud-based training solutions. I'll skip the applications. So we have two main settings in federated learning. First of them is cross-silo federated learning, where we have a bunch of organizations or companies, they're trying to collaborate in order to solve some machine learning problem. But the thing is, they can't share the data directly because this might be some medical records, but they want to train some global joint model. Then another thing, which I'll be focusing today, so that's the cross-device federated learning, where we have a center server that orchestrates millions or like 100 millions of devices, which might be different like IoT devices or some mobile phones. And each of them has a small amount of data, and they want to train some, let's say, recommendation model of some sort. And one thing also we have to keep in mind here is that the model that we are going to train is also going to be deployed to those devices or a similar kind of devices. How we usually train is the following. So we have some estimate of the global model that's communicated to the set of available devices that perform local training. Once then they compute update, send this back to the server, and that perform aggregation, obtain the new model that is to be communicated in the next round. So one thing that maybe people do not discuss very often is that, especially in cross-device federated learning, there is a large heterogeneity in devices. So what we see is that we see devices all the way from some low-end IoT devices all the way to some large, let's say, last generation mobile phones, or even beyond that. But the standard approach in the literature was that, okay, what I'm going to do is I'm going to run exactly the same model on each of those devices. And therefore, what you have to kind of respect is, okay, if I want to train some really complex model, I either have to drop low-tide devices, or I have to limit the global model size such that I can train on all of those devices and I can get reasonable speed. But all of those approaches, they have several drawbacks. When we, let's say, look at dropping low-tide devices, by design, we just limit the participation. And this is quite an issue in federated learning, because usually what we assume about the data they are very heterogeneous. So by limiting the certain subset of the clients, we actually might lose quite a lot in terms of what we are able to learn. On the other hand, if we limit the global model size, we also know that usually the bigger in terms of number of parameters and in terms of compute we go, usually the model has a better performance. But if we actually going to accommodate our model to the least performing device, we might end up training, let's say, logistic regression with very limited number of features that we can use. So therefore, what we decided for this study is that we'll try to actually overcome these issues. And there were two things that we put as our goals. First of them is fairness in participation, meaning that everybody can participate and we're going to take into account all the data. And the second thing is that based on your local constraint, we guarantee, or we're going to construct our model in such a way that you're going to get the competitive performance with respect to your local, or let's say your network constraints. All right, so how do we do that? Is first, I guess the most simplistic idea is we first gonna forget about that every single model has to run, every single client has to run exactly the same model. So what we're gonna do is that for lower tide devices, we're gonna deploy some kind of like the silly models that are accommodated based on what they can process. So let's say for those lower first generation like IoT devices, we're going to deploy something very the models with small width, while as we get more compute or better bandwidth, we can deploy wider and wider models. And this is all accommodated based on the memory, computational capabilities, and other parameters. So now the idea might be straightforward, but now the question is, how do we actually train such models that we can just simply prune and still expect the reasonable performance? And this is where this approach that we propose in the paper called order dropout comes into play. So how does that work? Okay, so here for illustration, I have a two hidden layer fully connected network. Here is the network, just simple forward pass on the full network. I guess all of you are aware of random dropout that works in a very simple way. So if for the layers that we deploy random dropout to, we look at each neuron with some given probability. We either drop it or keep it, and by dropping, we remove all its incoming and outgoing connections in the forward and backward pass, and that's how we're going to do the evaluation. For order dropout, and one thing to say here, so for random dropout, so the idea is here that we're going to regularize network such that we kind of prevent the co-adaptation in the certain layers, such that we actually improve the generalization of our model. For order dropout, here the kind of the motivation, apart from regularization, is slightly different. So what we are trying to force our network to do is, so how we order dropout is parameterized by two things. So we have a set of width. So this would be numbers between 0 and 1, which is which are the width on which we want to evaluate the model. And then we have some distribution over this width that we're going to use for the training. So what we do here is in every single step for the training, we just sample from the distribution. Let's say we sampled here 0.4. And what we're going to do for all the layers that we apply dropout to, we just keep 40% of the width, meaning here 2 out of 5 neurons. And this is how we're going to evaluate the forward and backward pass. So the hope here is that by construction, we kind of gonna enforce that networks perform as good as it can, more on the left side of the network. And to make this more formal and kind of show you that it makes sense, let's look at, so once we have this, then the deployment is very easy. Once we have the model that we can just simply prune, we can accommodate the model that we're going to deploy based on the capabilities of the device. So now the question is whether does it actually make sense? And does what we do is in some sense meaningful? So since it's quite hard to do theory in terms of general deep learning, we're just going to look at this simple proxy, which is we're going to try to fit a linear mapping A with one hidden neural network, fully connected neural network with no activational biases. And so this proxy is, in a sense, it's very simple, but still good enough in the sense that this is actually like just fitting the linear mapping. It's non-convex, non-smooth problem. So in a sense, it's somehow good, but still analyzable. So if we now we know that there is this linear mapping A from features to the output. If we have enough variability in the data, then we only solve the problem if our network can actually recover exactly this mapping, right? So now the question is what happens that when we throw in order dropout over this hidden layer. And it might be not surprising because I already included SVD here. So the thing is, what it does, it's quite straightforward to show that it regularizes the set of optimal solutions. And in order to solve the problem, so there is actually only one optimal solution up to scaling, and that solution has to recover along every width. So let's say along every width k, here 3, it has to be the best 3-rank approximation of this mapping. And this is not only in terms of that the set of optimal solutions is like that. One can also show, we have a follow-up that showing that actually once you run SGD, it will converge to such solution. And the nice thing is there, so all of this holds up to scaling. But the thing is SGD will take care of scaling. So you kind of don't have that problem. So in this sense, we can understand that this order dropout technique is also well motivated from the theoretical point of view. And now the next question is how to actually deploy it in the federated learning setup. And that will be quite straightforward. So what we first do is we have a set of devices that have a data, and we're trying to learn the model that's going to be eventually deployed to those devices. So we first ask for any standard machine learning, we choose the architecture. Then we choose what are actually the width based on those devices that we see that we're going to train on. The distribution, what we did is actually usually quite straightforward. You can use uniform and it's going to work. So for instance, here, what you see that the different distribution that I take, for instance, if I take resident 18 or cipher, along every width, the model has decreasing number of parameters with decreasing this p-value, which is width, not what p-value in statistics is, and also the decreasing number of megs that you actually have for doing forward and backward pass. So in order to make it a bit more simplistic, what we do first, we do some kind of clustering where we cluster the devices into several tiers, and then each tier is assigned with some p max values, which represent the maximum width that clients in this tier can evaluate models. For instance, here, they can only evaluate model up to width 0.3. So what we then do for the training, this is a standard training loop in federated learning. We just choose all or subset of available clients. We have a global model that's communicated to the clients, but the difference is that we communicate the model based on the capabilities of the client. Then you take any popular solver, any of your popular solver, then you run, let's see, once there were several local steps, but you have to add this order dropout, and here the distribution is such that you always select the smaller or equal model. Then you obtain the update, communicate back, and you have the new global model. So, and here the difference is you also have to do the aggregation in a heterogeneous way, because those models that cannot handle those clients that cannot have a full model, they actually can't contribute to the part that they can handle. So you have to actually reflect this in the way how you aggregate. All right, and then for the inference, so we already trained the model without the dropout, so we know that we can actually for free without any data, we can just evaluate it on different width. So you just deploy based on the current capabilities. And what is a nice thing about actually having a model that is already pre-trained, or it's pre-trained such that it can be evaluated on multiple widths, is that, let's say I'm this device, I have my local model, but the thing is now I have very low battery, meaning that I actually can't, but I still want some reasonable prediction. I can actually make the model thinner, and it's still meaningful to evaluate that. So I have that for free, and I don't need any data for that. That's actually why we do only single p-value, and we don't do p-value per layer, because then actually you would need to be quite clever how to do the pruning for the model. All right, and then one other thing that I wanted to discuss about one nice property of or the dropout and aggregation for federated learning. This is regardless of whether you train on heterogeneous devices or not. One thing that people observed, and it's kind of widely known for linear for neural networks, is that if you have, if I take neural network, I take any hidden layer, I just shuffle the neurons, the output of the network doesn't change. But the thing is, it means that if I do just simple naive aggregation of the models that are all of them are optimal, just each of them is just a simple shuffle of the other model. I do the aggregation that can have actually quiet bet that can decrease the performance in the average model quite a bit. And there are techniques to actually prevent that, kind of to do some kind of neuron aligning before the aggregation. But the problem with those are that you can't use, for instance, things like secure aggregation, because you have to reveal every single update in order to align them. And also it's actually quite expensive. You have to have several communication rounds to kind of align the models. But what you can note here for order dropout, this is not really the case, because we changed the objective. And when you do the shuffle, you suddenly, your objective also, like your objective doesn't reflect that. So the output of along the width changes. So here, and we have some preliminary study on that, that is actually, it's even helps a bit in terms of like when you train even no heterogeneous network, no heterogeneous devices, you just train with order dropout, you get a better performance within the same communication budget. And that also kind of, what it gives you, what we observed is that when you run with order dropout, you can run more local rounds, because the kind of the model stays in a sense convex in terms of aggregation. All right, and now let me just showcase you some of the experiments. So first, just as a sanity check, we wanted to evaluate this on the non-federated learning experiments. One thing that I haven't actually discussed about, but it's kind of natural extension to what we have, is one can actually employ knowledge distillation, because we have like natural teacher, which is this full model, and those smaller models, they can be so the full model is a teacher, and then sample model is the one that you're trying to reflect the output. We evaluated on standard benchmarks, and what we took as the baselines for these non-federated learning experiments is just end-to-end trained submodels that are trained fully in isolation. And then also, like, naive idea might be that actually, like, if you just train your model, it might be even good on, like, you can choose random subset, and maybe it's still good. Maybe just what we do with order dropout, it has nothing to do with how well will model perform when you kind of shrink it in the size. But you'll see that it's actually not the case, and the order dropout kind of takes care of it. And for the distribution, we evaluate on the set of 1/5 and 10ths. So for this first experiment, when we compare it to the best single model, so this is trained model from the scratch, and these 5 models here are independent, and this is our model is, this is a single model evaluated on multiple width. And what we do here, so what you see here is the performance along the width is quite comparable to kind of the best what you can hope for, which is maybe best is not the best world here. But the thing is, because we don't see much of the effect of this regularization that comes to our model with our dropout. So we will try and what we do here is we actually employ quite a naive training strategy. We just take the best parameters for the full model and then train our order dropout with that. So there might be actually quite a lot of that we can improve there. Then when you actually compare, or what if I actually just prune my model with random dropout, and you see that this decrease is quite significant. So here, like 20 to 40% is almost unusable. And then also another nice property of order dropout is that you can increase the granularity and it still works well. So the performance is still good. And for federated learning, the same data set, only in their federated versions. And for the baselines, what we do is the only baselines that we find in literature at that time was on the federated dropout, which is actually that you try for those least capable devices, you just send them the model that's obtained by the dropout. We extended that to actually to drop out adaptively such that you match you choose the dropout in a way that it matches the capabilities of the given client. And then we said we created 5 client clusters where the Pmax is 1 all the way up to 0.2, and each cluster has 20% of the devices and the same distribution. So we can note here that when we train with order dropout, this would be like the best single model obtained with this adaptive dropout, which is our version of that we propose in the paper as a random dropout, because random dropout would be actually way lower because the models cannot tolerate large numbers of random dropout. Once you go random dropout beyond 10%, that's almost completely destroys the performance. And that's what you can actually see, that we have actually bigger model, bigger capacity, but because it has to be trained on lower capabilities device, we don't see always the improvement of the model, while this is not the case for FjORD. This is our and this is because of its natural structure. So natural ordered or nested structure. So we always see that there is an improvement in terms of the accuracy that we get. And then just to replicate the same experiment that we did, so also the scalability works even when we are in this more challenging federated learning setup. Okay, so just to summarize, so we discussed one of the key challenges in federated learning, which is heterogeneous devices. And to alleviate this, we proposed order dropout as a technique to enable heterogeneous training. And we also extended it to introduce FjORD, which is a federated learning method for federated device for heterogeneous device training that builds on top of order dropout. Thank you.
Any questions?
It's a very interesting approach. I have just a question. So do you need to make some assumption about the distribution of the devices? So isn't, for example,
what do you mean bias here?
So for example, the fact that for your network, depending on, for example, if you have a large amount of devices with small capacity with respect to the others, so could it be that that the training would be heavily biased toward the task?
Oh, okay. So you mean towards the, let's say, let's say here, that if you have any devices that belongs to this class, this is a question that actually the training will be biased towards this model.
Yeah.
So the thing is, what we observe is that's not really the case because the way how we train. So what we always do is, let me just go back. So the training. Yes. Yeah, so here, yes, here. So the thing is, you always train also the smaller models. So in that sense, actually the smaller models are always trained kind of in the best way possible. The problem is if you have many devices that cannot train the large portion of the model, then what happens, and we have the experiments in the paper, is that you can't really push this guy that high. So what you would see is that if there is actually more devices that can evaluate only the small portion of the model, then actually this one you have a slight decrease, but that's also but that's kind of expectable because those that part of the model that corresponds only to these guys is not that often seen. But the thing is, you still have nice like increased curve. So in a sense, you still have for the most capable clients, you have the best performance. But we have actually like one technique to alleviate, to kind of to shift that performance more, like to increase these guys by actually combining oil dropout with the small amount of random dropout to actually train a bit wider network. So kind of to try to combine those two ideas. But when you're employing random dropout, you have to be very careful because like once you go beyond like 10%, this is what you see. That is actually, it's having a larger model doesn't help you.
I have a quick question. Does the way, so you're guessing it's not like a uniform sampling across layers, or it's the peak was 0.1 doesn't mean 0.1 in every layer.
Actually, it means that. That's what we actually did. That's a very, so the thing is when we are trying to now extend it with is like trying to figure out which ways or which layers are actually more important. So, but the good thing about that is that even that naive idea actually works well. So you see, for instance, yeah. So even if you do it here, yeah. So even if we're here, like let's say on the here we actually use like we prune also like convolutional layers, which are usually considered to be the most important for like this cipher 10 plus CNN. But even with them, the training is pretty good. So for instance, here, like 0.2, like with 0.2 usually means that we only keep 4% of the network in terms of parameters, and it still performs very well. So that's, and we are like, yeah, so we are thinking about to extend it such that you can try to figure out which layers are important and maybe even boost like the performance of those like the small ones. But the thing with that is it's actually in order to figure it out, you have to introduce multiple parameters. You have to do search, and in order to do search, you need extra data, like you need some validation set. Here, by introducing just single parameter, we don't need to care about that because there's nothing to search. Thank you.